Hello students, in this video I'm going to be talking about proving line segments congruent. So one of the reasons why I love math in general is because math is actually the purest form of philosophy. It is based off of some very fundamental things, and then from there we are able to create and further infer more abstract ideas based off of those simple concepts. So what do I mean by this? Well, in geometry specifically, we will be working off of 5 axioms. An axiom is something that we find evident and accepted as being truthful. So these things we sort of take for granted, actually, because we've already assumed it to be true to begin with. So what are they? The first one being is that if you have 2 points, right, we can draw a line between them. And every line is a straight line, by the way. There's no curved line. A curved line is simply a curve. A line is one that is perfectly straight. Okay, so the first axiom is a line may be drawn between 2 points. So we accept that as being true. We don't give it a second thought. The second axiom that geometry is built off of is any line segment may be extended indefinitely. So if you have a line segment, meaning if you have the 2 points there and you draw that line between them, you can extend that line segment in either direction, going on forever. Again, we don't give it much thought. Axiom number 3, all points on a circle is r distance away from its center. So what this is saying is when you draw a circle, the distance between any point on the circle to the center, that is the radius. Again, we don't give it much thought when we think about these things, right? However, in this very philosophical discipline, we do need some foundation to be building off of, and that's what we're getting at right now. Axiom number 5, all right angles are equal. And that is absolutely true. A right angle is an angle that measures 90 degrees, and we know that all right angles will measure 90 degrees. They will all be equivalent. The fifth axiom is one that is a little harder, a little more challenging to digest. Let's just take a moment to read through this. It says that for any given point not on a given line, there is exactly one line through the point that does not meet the given line. So what this means in translation, just to break it down, is saying that if you have a pair of lines that is parallel, they will never ever meet. So again, it is very challenging to prove. Actually, yeah, that's right. It is very challenging to prove this. So which is why we consider this to be self-evident as being true. That if you have a pair of lines that are parallel, they will never ever meet. Okay, so these are some the 5 main ideas that we are going to be building off of. But we can't just have ideas like 5 individual facts. We need other things to help us make connections between these 5 things. And to do that, we need something called postulates. Now, a postulate is a logical statement that is accepted as true. And we're going to get into some postulates in a moment, okay? But again, it is a logical statement that is accepted as true. You may be thinking like, wait a minute, Mr. Chan, aren't these logical statements, right? A straight line may be drawn between 2 points. That seems very logical, doesn't it? Well, that's slightly different, though. What a postulate is, it allows us to connect the axioms together. And by connecting the axioms together, we can then form other things. And you're going to see in a moment why these postulates need to be present in order for us to use the axioms. The second thing that we are going to be using in order to, again, create and to build off of existing ideas is when we take the axioms and the postulates and put them together and make inferences, we then can make certain conclusions. And those conclusions are what we call theorems. So a theorem is a logical statement that is proven to be true. So really important distinction here between a postulate and a theorem. A postulate is an idea or a logical statement that is accepted as being true, as being factual, right? There's no reason to argue against it. Whereas a theorem is something that has to be proven, okay? And I want to get into some of the differences between the two. So a really famous theorem that everyone should have been exposed to by now, having gone through Algebra 1, and being that you guys are in geometry, is this guy right here. This is a really famous theorem. Anyone recognize this, right? A squared plus b squared is equal to c squared. That's a Pythagorean theorem. This is a logical statement as well. Now, if you were to tell a person that's never seen the Pythagorean theorem before, right, they would have no idea where this came from. So, which is why this statement requires a proof. And we're going to get into proving this, not in this lesson, but in later lessons down the line. So this is the Pythagorean theorem. Now, what exactly is a postulate? So this is an example of a postulate, a segment addition postulate. So let's just take a moment to digest what this is saying. If I have segment AB and segment BC, and I add the two segments together, then these two segments are going to form segment AC. This statement requires no proof because we accept this as being factual, as being true. If we have these two line segments and they are on the same line and we place them together to form a new line segment, then of course we are going to end up with a longer line segment. That's all this is saying. This is the segment addition postulate. Similarly, then the next idea I want to introduce is this idea of congruence versus equality, right? Notice I have here that I have AB plus BC is equal to AC. Well, the reason why I say they're equal is I'm talking about they're equal in lengths. They're in geometry, you're going to hear the use of the word congruence or congruent to. So when two things are congruent to one another, it is described as being exactly the same in every way, identical in every manner. So when two things are congruent, they are not just equal in value, but they're equal in every way. Okay, and right now it seems kind of strange to be thinking about to be talking about line segments, right? Because there's only really one dimension to be measuring here, which is length. But when we talk about more abstract ideas, there is a small distinction between congruence and equality. However, I will say this. For our purpose in this course, even though there is a small distinction, we are going to be treating this idea of congruence and equality in the same manner. So even though in a problem it may ask you to prove something to be congruent to another, right? We are going to be treating congruent things as equal things. It seems rather abstract right now. You'll get the hang of it when we get into an actual problem. But again, there is a small difference, okay, between the two. And the difference is when we talk about equality, we're really talking about the quantifying specific things about the two objects. Whereas congruence is saying everything about the two things are the same. Again, just to reiterate some of the ideas that I've mentioned there, when we talk about two things being congruent or describing congruence, is two objects are congruent if the two objects can be superimposed onto one another. So imagine this: you have like a pyramid, right? And you have another identical pyramid. The two pyramids will be congruent to one another if you can take one and place it right over the other, and every point on the two pyramids match up perfectly, right? So therefore, the two pyramids are going to be congruent. We can describe this idea of congruence for any object. Okay, two cars are congruent if you overlap the two cars together, where every point will match up. Remember, every point has to match up in order for the two objects to be congruent. Equality, when we talk about equality, two objects may have equal lengths, angles, and sizes. So here, when we talk about equality, we're really quantifying specific things about said object. So we can talk about their lengths being the same. We can talk about their weights being the same, right? Their lengths being equal, their weights being equal, the height being equal, and so forth. So there is a small distinction between the two. However, for our purpose, for this course, we're not going to really make that big of a deal between the two ideas. Just one further word here, equality involves numbers, whereas congruence involves shapes. You don't say two numbers are congruent, just as you don't say two shapes are equal, right? So again, just pause a moment and think about it. You don't say two numbers are congruent. You say that two numbers are equal. You can, however, say two shapes are congruent, right? Because we're talking about everything about the shape, both their length, the size, the shape, right? So that's the real distinction between the two. Again, just to reiterate, for our purpose in the course, even though there's a small distinction between these two ideas, when we go through problem solving and going through proofs, we're going to make no distinction between the two. All right, let's get to one of the first problems here. So you're given that ON is equal to 7, TN is equal to OY, TN is equal to OY, which is equal to 15. And we need to prove that TO is congruent to NY. Oh, and one more thing, that TO is also equal to 3x. Okay? All right, so with that understanding, let's create a two-column proof. Because, again, this problem here is asking for us to prove that those two segments are congruent. So how are we going to do that? So what we're going to do is we are going to first write out all the givens. It appears I may have left out a given here, so my apologies for that, and which was ny is equal to x plus 4. That was a part of the given that I had forgot, or that I had concealed and not revealed. Okay, so ny is equal to x plus 4. That was a part of the given that I had left out there. Okay, so how are we going to do this? Well, one of the things that I notice is that there's an overlap between TN and OY, and we know that TN and OY are both equivalent to one another in length, right? So one of the first things that we can say is, or actually, one of the things that I as a strategy, okay, if I notice that there are segments and they're formed by other smaller segments, I would want to maybe perhaps write out that relationship. So I can say TO plus ON is equal to TN. And why is this true? Well, this is true because of, again, this is a logical statement. It does not require any proof because of segment addition postulate. I can also say the same thing about the other segment, OY, which is, again, ON plus NY. Oh, I'm sorry, I skipped a step there. So once I know that these two segments add up to TN, I can perform substitution, very similar to the algebra proofs that we did in the previous lesson. We can then say 3x plus 7 is equal to 15. Right? And this is because of substitution between lines 1 and 2 into line 5. We can do something really similar to, again, to the other segment now, OY. Right? So we can say ON plus NY is equal to OY, again, because of segment addition postulate. And very similar to step 6, I'm going to make a substitution. Right? What was ON equal to? Oh yeah, ON was equal to 7. And what was NY equal to? It was equal to x plus 4. And what does OY equal to? OY equals to 15. So again, we make the substitution. And again, this is because of substituting lines 2, 3 into line 7. I actually left out one other thing. It's not just 1 and 2 into line 5, and it's not just 2 and 3 into line 7. It's actually 1, 2, let me use a different color here. It's 1, 2, and 1, 2, and 4, right? 2, 3, and 4 all into line 7 because I substituted 3 things there. It's not just 2 things. Okay, so we made those substitutions. Okay, and notice now, because line 6 and line 8, they both equal to 15, right? And we also know that Tn is equal to OY, right? From step number 4, we can make another substitution. We can say that TO plus ON is equal to ON plus NY, right? Let's just pause a moment if you don't see this. So again, I know that Tn is equal to OY, and again, Tn and OY can be expressed with TO plus ON, and OY can be expressed with ON plus NY, so therefore I can make those substitutions down here, right? So this is true because I am taking lines 4, I'm taking lines 6 and 8, 5 and 7, and substituting it into line 4. So now that we have it up to this point, our objective is to prove that TO is congruent to NY, and we have all these numbers to work with, right? I can say TO plus ON equal to ON plus NY. I can make substitutions again, right? Since I know that TO plus ON is equal to 3x plus 7, and I know that ON plus NY is equal to 7 plus x plus 4. This is because of substitution between lines 6 and 8. Since they both equal to 15. And then I can subtract both sides by 7, right? But in order for me to subtract both sides by 7, I need to say 7 equal to 7. And then I can subtract lines 10 and 11 together. And I will end up with 3x is equal to x plus 4. So again, 7 equal to 7, that's because of the reflexive property. Okay. And again, we are going to try to isolate x, but in order to do that, I need to subtract things over, so I will need to apply the reflexive property again, saying x is equal to x because of reflexive. And then we're going to subtract lines 12 and 13. So we got 2x is equal to 4, and that's because subtraction between not 10 and 11, my apologies here, my goodness. This should really say lines 12 and 13. Okay. And then we are going to be dividing both sides by 2, right? So we say 2 is equal to 2 for reflexive, and we're going to take, again, lines 14 and 15 and divide them together. We get x is equal to 2. So this is 12 minus 13. Okay. And since we have x is equal to 2, we can now solve for what TO and ON is, right? So TO is equal to 3 times x, so we can say 3 times 2, which is substitution. So we're substituting information from line 16 into all the way back into line 1. We multiply, TO is equal to 6. And we are going to find out what NY is. NY is equal to x plus 4. So again, 2 plus 4. And that is 16 to 3. Line 16 all the way back to line 3. And we have NY is equal to 6 because of addition. And since we have TO is equal to 6 and NY is equal to 6, we can then conclude that TO is congruent to NY. And that's because of substitution. So really, technically, what I should have written was TO is equal to NY, because both of these statements right here, right now, they're saying that TO is equal to a certain segment, NY is equal to a certain segment. So what should have happened in line 21 is TO equaling to NY, and then line 22, I would say TN is congruent to NY because of the definition of congruence. But one more time, for our purpose, we're going to skip that step, okay? So the final statement, the final step is TO is going to be congruent to NY. Okay, because we know that two segments that are equal in length are going to be congruent to one another. So that's why we are going to skip that last statement there. But technically speaking, yes, we should have made that distinction. But again, for this course, we don't need to do that. Okay, so what I'm going to do now is, if you notice in the given statements here, right, I took away all those numerical values. I took away, ON equal to 7 and y equal to x plus 4 and 15 here, right? In this two-column proof here, it's the same exact setup. The difference is, one more time, so again, I'm going to get rid of this, I'm going to get rid of this, and I want to get rid of that. The only things that are given right now is that Tn is equal to Oy. That's it. Okay? So from there, we need to prove that TO is congruent to NY. I'm sorry, I forgot one thing, that TONY is a line segment. That is important too, because all these points, if they weren't on the same line segment, then then all the things that we're about to talk about, or the things that we talked about in the previous problem, would not have been true. Okay, so again, TO and Y, all those points are on the same line. And right now, we're going to try to repeat the problem, and we're taking out all the numbers, and I want to show you that actually we end up with the same conclusion, even though we're not working with any numbers. So how are we going to do that? Well, again, I want to go through a very similar process. Since I know that Tn is equal to Oy, I know that Tn is made up of To and On. That was one of the first steps that we had taken. We are going to go through this very same step. And this is true because of the segment addition postulate. We can do the same thing with the second half of that of statement number 4, which is what Oy is made up of. Oy is made up of On plus Ny, and that's because of segment addition postulate. Since I know that Tn is equal to Oy from line 4, I can make a substitution between 5, 6, and place it into 4. And I can say TO plus ON is equal to ON plus NY. Again, this is because of taking information from lines 5 and 6 and placing it into line 4. Lastly, notice that in line 7 I have ON on both sides. Well, since I know ON is congruent to itself or is equal to itself, I can say reflexive. And again, I want to subtract line 7 and line 8 to get TO is congruent to NY. And that's because of subtraction between line 7 and line 8. Again, line 9 should have said TO is equal to NY, but like I said before, we're not going to make a distinction between equality and congruence. We're going to treat them as synonyms for this course. So final conclusion, again, TO is congruent to NY, which was what we were trying to prove. So can you see, oh, I'm sorry. Yeah, so can you see that the second approach here is actually much simpler, right? There are less things for us to work through. There are less problems as far as like algebra goes. Well, that's because the algebra wasn't necessary. I hope that if you maybe perhaps pause the video and go back and look through the first problem together, you're going to see that much of the numbers didn't really have to be there. I hope that you guys were able to make that conclusion for yourself. And I'm really proud of you guys for going through your very first segment proof. You know, let pause the video, rewatch it, and try to attempt it again if this didn't make sense. And come by during office hours if you have any questions.